this. So let me just say insensitive to lambda. And here too, insensitive. How could it happen? It's a very sensitive function of lambda and these two parameters, and it's a very insensitive function of these two, it's a insensitive to lambda function of these two things that you can go out and measure. How could it possibly be true? Sensitive to lambda, but when written in terms of A and B, insensitive to lambda. There's only one way, logically, that this could happen. A and B themselves are very sensitive. A and B are two examples of the C, the general observer. A and B are very sensitive to the cutoff. But I go and measure them, and I take them as my inputs for calculating everything else. And everything else, the only strong dependence it has on lambda is through A and B. But I've just gone and measured them. It's 5 GeV, or whatever that A and B are. And then that insensitivity is gone. Okay. So this whole procedure is really a way of making the observation that it's a way of bookkeeping the sensitivity of the cutoff. You can, if you want, say, this is the action, the only action I've ever heard of, and I have a cutoff, and I have tremendous sensitivity to the cutoff. But what's the nature of that tremendous sensitivity? The answer turns out to be that sensitivity comes in every observable, A, B, C, D, whatever it is, but there's sort of two independent directions. And so once you measure two of these observables, as long as you haven't been too stupid about choosing them to sort of span all the possible UV sensitivities, every other measurement is an insensitive, cutoff insensitive function of those two measurements. Okay? So it's the trade of who are your independent variables. Are you going to make your independent variables some abstract thing in a path integral that you never go out and measure? Or two things that you can measure and then predict everything else? And if you take this approach, then you're insensitive to the cutoff, and you can, in fact, take the cutoff to infinity and say you define your theory as a way of correlating observables, which is all that we ever want to do. We are correlating an infinite number of observables in terms of just two inputs. Okay? So that's the game, and this is what I mean by the passive observation, that these without ever mentioning the renormalized parameters, just thinking in terms of bare ones, you can think of it as simply A and B incredibly sensitive to lambda, C also incredibly sensitive to lambda, but it's an insensitive function of A. Then what is all the renormalized junk for? It's just to show that this is the case. Okay. And it is to make the process of so I think this came up once before, that while this is conceptually the cleanest way of saying what you have achieved by renormalization, correlating observables in a finite set of relationships, an ultraviolet finite set of relationships, writing things in terms of some couplings, as finite functions of some couplings, is a very useful thing to do. And so it is a kind of intermediate step for convenience, for human convenience, okay, which is what we're going to spend some time on. Okay, let's see, which gap should I fill in our logic so far? Yeah, so let me start with, why is it, all we know is that, oh,
I was just going to ask, so to get this renormalized action, we eliminated local divergences.
Yep.
So that rid of UV and sensitive parts, but couldn't there still be UV convergent terms left over that would only go away when you took the cutoff to infinity?
Exactly. So, when I say, so there are things which are insensitive to the cutoff, but insensitive to the cutoff means that, which means insensitive, if you have an insensitive, so here's an insensitive function of the cutoff. 1 minus 1 over cutoff squared. Or let me say energy squared. Energy of my experiment squared over the cutoff squared. That means that this is approximately 1 if your energies are smaller than the cutoff. So if you're imagining a cutoff, vastly bigger than your experimental energies, then you can say, oh, I want to keep that, even though it's insensitive, it is a function of the cutoff. But the very word insensitive means, insensitive to large cutoff means that the limit of the cutoff being infinity is actually a good approximation to the truth. But then it can actually be read another way. And so that's the way an effective field theorist thinks about it, which is there really may be a cutoff, but I'm positing that it's big. I have a win-win situation. If I posit that it's big, then I kill that possibility, and I take advantage of this simple calculability without having to know the details of the cutoff. And I can compare to experiment. If it works, I've succeeded. It's a triumph of quantum field theory. If it fails, I still say it's a success, because they say, oh, new physics is around the corner. And indeed, if you look at what the LHC attempts to do, or LEP attempted to do, and so on, or even these flavor tests, what are they attempting to do? They're doing complicated or normalized quantum field theory calculations. And they're finding tremendous agreement and success. But they are also hoping for failure of this algorithm. Because then it would mean the one place it has to fail is because the cutoff is, this term is not so small that you can neglect it. So it's giving a 2 decimal place deviation. And that means that lambda is a factor of 10 above my experimental energy, and we build the next machine and boom. So that's the way we're playing. But then there's another, that's the effective field theorist way. There's another way, which is to say, once I see that I can actually take the cutoff to infinity, I'm able to actually define a theory which doesn't have a cutoff by taking it as the limit of this sequence of effective field theories with higher and higher cutoff. And that's a beautiful way of defining the renormalized theory. What we really call the renormalized theory, the theory which needs no cutoff, because it is the limit of a set of theories with cutoffs. Again, very much like derivatives. The limit of a set of differences, of ratios of rise over run differences. But then we all say, look, there is something called the instantaneous slope, the instantaneous velocity, or whatever it is. Breaking it up into the limit of discrete differences and ratios of differences was your human convenience. This thing exists. So there are some loopholes in what I said. They're very small loopholes, that's why I could just say it. But let's just... So, well, let me do the easy one, which is just something I said is true. I didn't prove it, and I'm not going to prove it, but I just want to at least say it's a theorem. Okay? So there's something called, I don't know what it's called in general, but I think it's probably started life being called this power counting theorem. And it is something we proved the one-loop version of, which says that one-loop divergences are local. And this just says it's true at all loops, but with one sort of necessary nuance. So it just says that if a diagram, if a loop diagram has all subgraphs subgraph. If it has all subgraphs finite, so if a loop diagram has all subgraphs being finite, then it's only divergences are local. So what do I mean by a subgraph? A subgraph is where you just put a box around any you put a box on top of this and separate out something inside the box and something outside the box. There's a box. But better yet, here's a box. Inside the box is lying a subgraph. And this is the entire graph. Now the claim is that if a loop diagram has all the subgraphs being finite, then the only divergences that it gives rise to are local in form. We want locality because then we are subtracting something local so that this plus the original action combine to a bare action which has the standard local form, corresponds to a standard Hamiltonian, and life is good. Okay, this locality is in that sense. It's crucial that the form of this doesn't change this, so this separation then looks artificial. It is artificial, and all we're doing is passively observing the moral of this story here. So we want this locality, but it's not always true. I need that all subgraphs are finite before I can say that the whole thing has this local form. First, have we seen, so this is now, we proved this at one loop. The reason is that at one loop, the only kind of subgraphs that you can draw, the only proper subgraphs, meaning not the entire graph itself, the only kind of subgraphs you can draw are necessarily tree graphs. And the tree graphs are obviously finite, and hence this theorem says the divergences have to be local. But guess what? We proved that all one-loop contributions to gamma are local by this differentiation and integration process. So we have actually done the hard work in that case. Why is it, and what is it pointing to when it asks, but in higher loops, clearly this clause is non-trivial. And we have to ask, why couldn't things just go like one loop? What was the problem? And it's easy to see what it is that is the sticking point. Consider this diagram in phi to the fourth. This diagram has three propagators going like 1 over p squared and an integral d4p. So in fact, this diagram is finite. It's one loop, but it's also a finite diagram. It doesn't need much help. Okay? But what if I did this? What if I made a two-loop diagram that looked like this? Well, in this case, this loop is actually finite, but this loop is divergent. It's got two propagators going like 1 over p squared each, and then an integral d4p, so it's a logarithmically divergent diagram. So this one is diverges. And you might say, let's just use the differentiation trick and then be able to see that the divergence has to be local. Okay. Well, let's say that this is P1 and P2, Q1 and Q2, and whatever, R1 and R2 can be by momentum conservation. You can get it. So we can imagine differentiating with respect. So let's take these as independent. Let's say this P1 is determined by minus P2 minus R1 minus R2 minus Q1 But we can differentiate with respect to all the independent momenta and try to make this thing converge. No, I think that will succeed. Let me try it, otherwise I'll think of a different example. So let's differentiate with respect to any of the external momenta to make it converge. Now, of course, this loop we can plainly see with our eyes. This loop is actually happy and convergent the way it is. So somehow we have to get these propagators and differentiate them in order to make it converge. Great. There's R1 and R2, and they're going through here. This is L, and this is L minus R1 minus R2 or something. Let's just differentiate with respect to some of these R's. Boom, we're in business. But the thing is that every time I hit a derivative of R, the R's are also flowing in here, right? So there's some LS minus R1 plus various other things. So if I differentiate with respect to R1, by the product rule of differentiation, there will always be cases where the derivative hits, say, this propagator and makes this even more convergent, not that it needed any help, and leaves this untouched, and other cases where it hits this and makes it converge. But there are always going to be terms where differentiation hits this or this or this with respect to R instead of this. You are not able to say any finite number of derivatives that you can hit the entire expression with that kills the divergence here. Okay? This is not like when I wrote polynomials in the Feynman integral. Because a polynomial, you hit it with a finite number of derivatives, eventually you get nothing. There's nowhere else to act but on the denominators of the Feynman diagram, of the Feynman integral, and that'll make it converge. But now, something like this, or something like this, the unintended propagator, I can hit it a million times and not exhaust it, the possibilities. And there will always be something in the product rule of differentiation where this integral survives intact and divergent. Okay? So it's a problem. We can see it right off the bat that there's something irritating going on already. Okay? So then it seems like, well, maybe there is a nice theorem that says that if only the subgraph didn't diverge, then I would be in business. But unfortunately, we are finding readily that the subgraphs do diverge, and so we are stuck. Okay. So the qualifiers, this should be read to include the lower order counterterms. Okay, I'm massaging what was probably the original form of the power counting theorem to make it as straightforwardly usable with our strategy. But basically, we should not consider this diagram in isolation. We should consider it with this delta lambda one loop counterterm. Okay. Because then this subgraph, which is irritating us by being divergent, we should add, when we say the subgraph, we should include the counterterms that would also be there in that subgraph if we added those diagrams together. Okay. This plus this, well, this delta lambda was chosen at one loop so that this thing would be finite. This plus this would be finite. It's in that sense that you should read the terms of this theorem, which says that now, in this case, the subgraphs are finite. Then the only divergences that remain by doing the entire graph are local. In fact, in this particular example, in this case, once you have conquered this subdivergence, as you can sort of see by eye, this loop is finite. So it's in fact, it doesn't have any local divergences once you've done this in this example. Okay. The other classic case, which I'm still debating whether to give you to do, but anyway, it's a two-loop diagram. This is not true. Again, you need this theorem to come to your aid, but you need to use, in subgraphs, you need to use the for this subgraph, there again is this one loop counterterm, so that you should really think of the subgraph as this plus this. And now there remains an ultraviolet divergence, even after you take the subgraph into account, and the subgraph is now finite because of this one loop counterterm. At two loop order, you will in fact incur a new divergence. It is possible, and it will be there, but it will be local. Okay. Now you can see why this theorem then sort of makes it possible to continue with the general strategy. If it was not local, I could not subtract a local action and get a finite result. And if it's not local, then I don't know in what way it corresponds to the usual form of Hamiltonian and the usual sense of unitarian. Okay? Whereas now we know that as long as you've normalized the theory by hook or crook up to order h bar to the n, at order h bar to the n plus 1, the only divergences you're going to get are local. Okay? So that's the game. Okay, I have to run. Unfortunately, this is exactly the kind of thing you would want me to ask many questions. So let's hold that till next time, but it'll give you a chance to at least play around with the idea of what could I have been saying, and what I'd like you to try and play around with is in what sense it's sort of passive, in what sense it therefore not doing anything except taking the cutoff to infinity and changing who is the thing you're using as the independent variable.